A very good morning to all students. I am Dr. Himabindhu in the Department of Mechanical Engineering, and today I am here to teach you the robotics subject, and my today's topic is Jacobian matrix. In today's topic, we'll see what is the use of a Jacobian matrix, what is the application of the Jacobian matrix, and how do we solve the Jacobian matrix in order to identify the end effectors. Jacobian matrix. What do you mean by the term Jacobian? Right? What do you mean by the term Jacobian? And what is it used for? Generally, any particular robot, which is having a Jacobian matrix, is a powerful tool. Any robot with a Jacobian matrix acts as a powerful tool for the programming of the robot in order to design any particular program, in order to write any particular robot programming. With the use of the Jacobian matrix, it becomes easy for us to solve the complex kinematics or dynamic statements, motions. Right? So, in order to solve any particular type of the complex kinematic or dynamic motion analysis, the Jacobian matrix is acting as a tool which makes it easy for us to write the robot program. So, this particular Jacobian matrix is being related with the help of the joint velocities of the robot, where we use both linear as well as angular velocities for its end effectors. Right? Where in the Jacobian matrix, we will be solving the matrix with the help of the joint velocities of a robot's end effector, where the joint velocities generally will be in terms of linear and angular velocities of the end effector, where we are used to plan the motion, or the motion planning is being done, or the control of the motion analysis or the optimization of the motion analysis will be done. Right? A Jacobian matrix is nothing but it acts as a powerful tool in order to write the robot programming, where we are finding any sort of difficulties to solve the complex kinematic or dynamic motion analysis. Now, these particular Jacobian matrix generally is being related with the help of the joint velocities, where the type of joint velocities which we use for the end effector are the linear and angular velocities, where it is used to solve the motion planning, the control of the end effector, or to optimize the end effector's manipulator of a robot. Right? Now, the Jacobian matrix generally is used to transform the vectors which are infinitesimal to one coordinate system to the another. Right? Generally, the Jacobian matrix is used to transform the infinitesimal vectors from one coordinate system to the other coordinate system. Right. So here in the Jacobian matrix, we also can compute the inverse kinematics. Right. The Jacobian matrix not only acts as a powerful tool for writing the programming, but it also is used to compute the inverse kinematics of the robot, where the function of the map that task space to the joint space, right? Where this particular Jacobian matrix is used as a task to space the joint space. And not only that, the Jacobian matrix is also used to affect the robot dynamics. Right? The Jacobian matrix is also used to affect the robot dynamics, as it determines the relation between the joint torque and the task force. Generally, the Jacobian matrix is used to determine the torque, force, and Cartesian coordinates of the end effector. Right? A Jacobian matrix is used to find out the torque and force being applied on the end effector, or it is also used to determine the Cartesian coordinates of the end effectors, where in order to find the torque and the force, we will be using the velocities of the robots, which are generally a linear velocity, which we determine by v dot, and angular velocity we determine by omega. Right? So using these particular two terms, we will be finding out the torque and force of the end effector using the Jacobian matrix, where Jacobian matrix is determined with the letter J. Right? Where the Jacobian matrix will be determined with the term J. Now, when we come across the Jacobian matrices here, we will be considering we are used to find out the singularities. Right? The Jacobian matrix is used to find the singularities as well as torque and force of the end effector. Now, these particular singularities and force and torque will be determined with the help of the joint velocities. Right? The Jacobian matrix is used to find out the singularities, torque and force of an end effector, where that will be determined with the help of the joint velocities. Right? Now, as I've told you, the Jacobian matrix is determined by the term J. So, the Jacobian matrix is equal to the velocities of the end effector, right? As we have seen here, the Jacobian matrix is equal to the velocities of the end effector, where this particular velocity will be determined with the help of the differential position. What do you mean by differential position? Yes, this particular velocities of the end effector will be determined with the help of the differential position. Differential position means nothing but differentiation. Right? By partially differentiating the end effector's position, we will be finding out the velocity of the end effector, whether it is a linear velocity or an angular velocity. We will be determining the velocities of the end effector by differentiating the particular end effector's velocity, with the help of which we get the Jacobian matrix. Right? So the easiest way to find out the position of any particular robo manipulator is being done with the help of differentiation. Right? So the easiest way to find out the position or orientation of any particular robo will be done with the help of the differentiation. For example, we have y1, right? We have y1, where we are writing y1 is equal to f1 of x1 comma x2, right? Whereas y2 is equal to x1 f2 of x1 comma x2, right? What are these generally called in terms of here we are taking y1, y2, and so on up to n number of constraints for the y-axis, where this is being written is equal to f1, that is force of x1 comma x2 and so on up to some n positions. In the same way for coordinate 1, coordinate 2, or frame 1 or frame 2 to n number of position. So these particular things are called as the position or joints of the end effector. So these particular two conditions are called as the position or position or joints of the end effector. So when we differentiate, in order to get the final velocity of any particular end effector, in order to find out the position or orientation or joints of the end effectors, as we've told, we have to do differentiation. So when we differentiate the above equation, we will be getting dou y is equal to dou f, dou y is equal to dou f by, this is dou f, right? Dou f by what is this in terms of x? Dou x, right? Dou x into dou x. Right, so this is the partial differentiation equation which we are getting. Now this particular above equation, when we write in terms of matrix, what we will be getting? Y1, y2 and so on up to yn, which is equal to the 3 by 3 matrix. If we are taking a 3 by 3 matrix into x1, x2 and so on up to xn. So this particular matrix, whatever we have got, is known as the transformation matrix, or we call it as a Jacobian matrix, right? So this particular matrix, whatever we are getting, is known as the Jacobian matrix. So now, when we come across the Cartesian velocities, the Jacobian can relate joint velocities to the Cartesian velocities of the robot manipulator. So, when we come across the Cartesian velocities, when we come across in terms of velocities, we get the equation as v is equal to px, py and pz. That is in terms of x-axis, y-axis and z-axis. Right? What we have told? Linear velocity and angular velocity, right? Linear velocity is v dot and angular velocity is w dot, that is angular velocity. So this Jacobian matrix, when we take in terms of Cartesian velocities of a robot manipulator, we write the equation as v is equal to, that is velocity is equal to pxyz, that is in terms of three axis system, is equal to the velocity matrix, that is the linear velocity and angular velocity, which is equal to j, Jacobian matrix, into theta 1 and theta 2. Right, that is theta 1 and theta 2. How are we taking that? For example, we have a digit surface and here we are taking one point, that is 0. Right, this is one joint, 2 joint and this is the joint 3. Right, so for these particular 3 joints, we will be having some certain angles, theta 1, theta 2 and so on. So this we are taking it in terms of Jacobian matrix, that is v is equal to px, py, pz is equal to linear velocity and angular velocity, which is equal to the Jacobian of the angles of the joints theta 1, theta 2 and so on up to n number of constraints. So generally, as I've told you, the Jacobian is used to find out the singularities, torque and force. Right? The Jacobian is used to find the singularities, torque and force of the end effector. So in order to find out these singularities, torque and force of the end effectors, we need to know first what do we mean by singularity. Before we see all these particular transformation matrices, we need to know what is a singularity, what do we mean by singularity, and what are the types of singularities we have. We need to find out. So singularity is nothing but it is a point where the robot loses its degree of freedom, right? That is, for example, we have 1, 2, 3 and this is an angle which is rotating at an angle of 180 degrees, right? So any particular robot which loses its degree of freedom at any particular point, it is a point where the robot loses its degree of freedom, is known as a singularity. Here, it is impossible to move the end effector in a particular direction regardless the joint. That is, we cannot move this particular end effector without the help of these joints, right? Without the help of these particular joints, we cannot move the end effector from one position to the other's position. So, when any particular point is losing its degree of freedom, that particular point is known as the singularity. Where here we have these particular points are known as singularity. That is, this is moving at an angle theta, this is moving at an angle some theta too. And when we are taking a linear directional robo manipulator, this is moving at an angle 180 degrees and so on. So these particular points where any particular point which loses its degree of freedom is known as the singularity. Now, no end effector, robust end effector will be impossible to move without the movement of the joints. Right? So here we have two types of singularities, that is the workspace boundary and the workspace interior. What do we mean by this workspace boundary and workspace interior? Workspace boundary is nothing but a robo which can be folded up and can be used, right? That is workspace boundary, and this particular robo will be at the boundary condition, right? This particular robo will be at the boundary condition. That is the robo which can be fully stretched, right? The robo which can be fully stretched and folded back, where the end effector will be placed at its boundary is known as the workspace boundary. And moving on to the workspace interior, it is nothing but the robo which is having two or more joints, right? The robo which is having two or more joints and which is being placed at the interior of the workspace is known as the workspace boundary. That is the the robo which is having two or more joint axes which would be placed at the interior of the robot's environment is known as the workspace interior. So before we find out the singularities and torque and force of any particular robot's Jacobian matrix, we will, as I've told you, we need to know about singularity. So singularity is nothing but any particular robot which loses its degree of freedom at any point is known as singularity, where we have two types of singularities, right? Now, based upon those two types, we will be solving various number of problems. So now, when we take any particular robo, as I've told you, when we have taken this particular type of the robo, right? Now here it is moving at an angle theta 1, theta 2 and so on. So here what is happening? It is moving from the position 0 to the position 3. Right, the particular robo is been moving from the position 0 to the position 3. So for each joint of the each joint of the robo, we write the Jacobian as Jacobian 3 at the joint 3, Jacobian 2 at joint 2, Jacobian 1 at the joint 1, and for the base of the robo, we write it as J naught. Right, that is for the base frame of the robo, we write the Jacobian as J naught, where this particular J naught is equal to the rotational matrix from 3 to 0. Right, rotational matrix from, we generally take from higher order pair to lower order pair. So the rotation matrix from 3 to 0 into this Jacobian at the joint 3, where this particular rotational matrix is known as the transformation matrix. So this particular rotational matrix is called as the transformation matrix, that is R3 to 0. So when we have taken this particular example, so this is one 2, 3, and 4. And this is the end effector. So this is moving at an angle theta, right? This is moving at an angle of theta. So theta is the angle where robot will reach its singularity. As I've told you, that is the point where it loses degree of freedom, right? So theta is the angle where robot will reach its singularity. So how will we find out this particular singularity? As I've told you, in terms of determinants of the Jacobian. So to find out the singularity, we need to find the determinant of the Jacobian. Right? To find out the singularity, we need to find the determinant of the Jacobian. So the determinant of the Jacobian of theta is equal to, when it is equal to 0, we tell that the singularity is existing. If the determinant of the Jacobian theta is not equal to 0, we tell that that particular robo has no singularity. That is, it is robust, it is rigid, it cannot have any particular type of the movement, right? So any particular determinant of Jacobian theta, when it is equal to 0, it is that particular robo is said to be under singularity condition, right? And any robo which where its determinant Jacobian theta is not equal to 0, then that particular robo is said to be non-singular, that is, it is robust or rigid. So how do we write this particular determinant in terms of matrix? It is nothing but theta 1, theta 2, so on up to theta n is equal to 0. That is singularity matrix, right? That is known as the singularity matrix. Now, how do we do the partial differentiation of this particular matrices? As I've told you, initially in the first slide we have seen y1 and y2, which is equal to f1 of x1, x2 and so on. y2 is equal to f2 of x1, x2, so on up to yn. So when we are, in order to find out the position of the end effector, right, in order to find out the velocity, we need to differentiate the position. So how do we differentiate the position? What is we are taking y1. So when we are differentiating, what we write? Dou y1 is equal to dou f1 by dou x1 into dou x1 plus dou f1 by dou x2 into dou x2, so on. And next equation, dou y2 is equal to dou f2 by dou x1 into dou x1 plus dou f2 by dou x2 into dou x2 plus so on up to dou yn, right? Up to dou yn we will be writing. So this equation will be written as overall dou y is equal to dou f by dou x into dou x. So this particular equation in the whole, we write it as dou y is equal to dou f y dou x into dou x. Now what is y? It is nothing but y1, y2 and so on up to yn, which is equal to the 3 by 3 matrix or any n number of matrix into what is x1, x1, x2 and so on. So this equation, whatever we have got, j is equal to the 3 by 3 matrix into x is known as the Jacobian matrix. This is known as the Jacobian matrix. Right? So the final equation to find out the Jacobian matrix is nothing but y is equal to j into x. Right? Y is equal to j into x, where j is equal to Jacobian matrix. So this is how we find out the Jacobian matrix for any particular equation which we get, right? Now we need to know what is the difference between a partial differentiation method and a velocity differentiation method, right? in partial differentiation, what we are doing? We are differentiating the equation, right? Here, this particular whatever equation we have did is a partial differentiation, right? So here also we have two types of methods to find out the Jacobian matrix. One is the partial differentiation method, and one is the velocity propagation method. Right, we have two types of methods how we can determine the Jacobian matrix. One is the partial differentiation method, and one is the velocity propagation method. In partial differentiation, what we are doing? We are differentiating the equation, that is dou y is equal to dou f by dou x into dou x. This is how we are writing the j is equal to y is equal to j into x. This is how we are determining the Jacobian matrix with the partial differentiation method. Whereas in velocity differentiation method, we will be using the linear velocities, that is v and omega, which will be equal to theta 1, theta 2. Right? So this is how we determine the Jacobian matrix into J, right? That is the EVE is equal to J into theta 1 and theta 2. Right? In the partial differentiation, what we are doing? We are taking equations y1, y2 up to yn up to n number of constraints, and we are partially differentiating that, and we are writing the Jacobian matrix as y is equal to j into x. Whereas in the velocity propagation method, we will be taking the linear velocity and the angular velocity, that is omega, and in terms of theta we will be determining the Jacobian matrix as w v and omega is equal to theta 1 theta 2 into j, right, at the initial condition, that is velocity is equal to Jacobian matrix into theta 1 and theta 2. This we will be finding out. So these are the two methods with the help of which we find out the Jacobian matrix, right? So these are the two types of the these are the two types with the help of which we find out the Jacobian matrix. Now, in this particular Jacobian matrix, again we have revolutionary joint, and prismatic joint. Right, this we have discussed already in the earlier class. Right, what do we mean by revolutionary joint and what do we mean by prismatic joint? Revolutionary joint is nothing but any particular robot's manipulator which is rotating in some particular angle is known as a revolutionary joint. Whereas prismatic joint is nothing but the in and out of the robot's manipulator, that is in the linear direction, is known as a prismatic joint. So this revolutionary joint is generally determined by theta, and the prismatic joint is determined by t. That is, here we will be finding out the torque, and here we will be finding out the force. Right? So in order to find out the torque and the force, we will be considering these particular two joints. That is, any particular joint with any particular robot joints which is having some revolution with an angle theta. There we will be finding out some amount of the torque. Any particular robot's joint which is taking the linear direction, that is prismatic joint, in terms of prismatic joint, right? There we will be finding out the force. In the singularity, we will be finding out the Jacobian matrix by partial differentiation or the velocity propagation method. And in order to find out the torque and the force with the help of the type of the joint, we will be finding out the torque and the force. Now, this in order to find out the torque and the force, we will be taking the equation as torque is equal to Jacobian at a base power t into F. That is, torque is equal to the base Jacobian transformation matrix into the force. Now, how do we write this? equation. How do we write this particular equation? It is nothing but T1, T2, T3. That is torque 1, torque 2, torque 3 is equal to the Jacobian matrix of the brace whole power T into force at x-axis, force at y-axis, and force at z-axis. So this is how you find out the torque and the force of any particular robot's manipulator and effector. Right? How do we find out the singularity? With the help of the partial differentiation or with the help of the velocity propagation method. And how do we find out the torque and force of the Jacobian? How do we find out the torque and force of the end effector of the robot? With the help of the type of the joint, that whether it is a revolutionary joint or whether it is a prismatic joint. So in the revolutionary joint, we get an angle of theta, and prismatic joint we get a linear distance of the robot's manipulator, where in revolutionary joint we find out torque, and in the prismatic joint we find out the force. And when we need to find out the torque and the force, we'll be taking out the equation as torque is equal to the base of the Jacobian matrix for the transformation into the force, and T1, T2, T3 is equal to base Jacobian power T into Fx, Fy, and Fz. This is how we find out the torque and force of the Jacobian matrix. Clear? Hope you've understood about the Jacobian matrix and how to solve the Jacobian matrix equation, whether it when it is in the singularity condition, or whether when it is in when we need to find out the torque and force of the end effectors. Clear? So this is all for today's class. Hope you've understood this session. Thank you. Signing off for today, Dr. G. Himabindhu.
Like, share and subscribe. Hit the bell icon for more updates.